About observations that need to be made during the cage and the concrete placement. So we're kind of, again, into the real world, off of the theoretical or the design stuff, and now we're boots on the ground again. So things that ought to be checked before the cage gets picked. Again, these are huge cages, so they're 9 some odd foot diameter cages, number 18 bars. So that's 2 1/4 inch diameter bars. There's 32 of them at Pier 1 and a little bit less at Pier 2. So these are big, significant cages. They weigh a lot. They can be difficult and dangerous to be around. When they're picking the cage, know the length of the cage and be 1.1 times that away. Things to check before the cage is being picked. Obviously, make sure the cage matches the plan. That's bars, number of bars, size of the bars, grade of the bars. Remember, 2 different grades. Grade 75 for the longitudinal steel. That's these bars, the ones that run up and down the column. Grade 60 for the hoops. Okay, so different grade bars. Make sure that the spacing of the cage itself is where it's supposed to be. The spacing is very important. We need concrete to be able to flow through it. Is the cage tied correctly? And so what that means is every lap we have between the shear hoops, the circles that go around the cage where they cross the longitudinal bars, that ought to be double tied. Every lap should be double tied, okay? And so the whole point is so that when the contractor goes to pick the cage, it doesn't rack, it doesn't roll over, it doesn't come apart. So double tied every lap, okay? So that's a lot of tying, but it's well worth it. Are there stiffeners? You can see this photo here. These stiffeners are installed. This is steel that does not remain in the permanent structure. That's simply to keep the cage from racking when you pick it up and get it stood vertical. When the cage goes in the hole, the contractor is going to want to cut those out. If the contractor doesn't want to cut them out, make them cut it out, because as your trimmy's at the bottom of the hole placing concrete, as they're pulling that trimmy up, we don't want it grabbing onto anything and pulling the cage up, changing the orientation of the cage. Okay, so we said, make sure the cage is to plan. The plans clearly specify what the openings need to be or what the spacing needs to be. If you see anything where the cage looks too tight, you know something's out of whack, so say something. Now's your time to do it when it's sitting on the barge or on the bank. Red Wing's not going to have CSL pipes. That's cross-hole sonic logging. Those are 2 inch diameter Schedule 40 steel pipes. Sometimes they're plastic, but they should be steel. We're not going to have any of those at Red Wing, but we will have tip wires. The pipes are a little more robust. They're steel pipe. Our tip thermal integrity profile wires are just electrical wires. Okay, so you got to be kind of careful of those. Orientation control. We got a slide in here. So Paul Gronvold is going to be very concerned about what orientation this cage or these cages get into the ground and where they get cast. Not all jobs are as critical as with the orientation. In fact, probably most are not quite as critical as this, but these are big shafts, and we've got a lot of reinforcing steel at the pile cap that's got to fit through these cages. So the orientation control is something that we have to be mindful of. All right, as the cage is picked, so make notes. Did the contractor pick it in a nice smooth manner, level manner, or is it a slinky that's got a 90-degree bend in it? Obviously, this is a good-looking pick here. They've got 2 different cranes pulling on this, so once you get it vertical, things get a lot easier, but make that observation. Tip wires, you can see, those are those yellow wires right there are the tip wires. Spacers, little wheels that snap onto the shear hoops. That's what keeps your cage in the center of the hole and gives you the clearance that are required per the drawings. So as the cage is being lowered into the hole, the guys are just clipping on these little wheels right here. They should have boxes of them sitting there before it goes in. Centralized, we talked about that. Removing the internal bracing, a question Paul Pilarski had. Yeah, so when they're lowering the cage in, they are cutting out the stiffeners. Now's our last chance. Double checking the CSL tubes, not for Red Wing, but for a lot of other jobs that will have CSL tubes and the tip wires. Checklist, very helpful tool. I mean, so you don't have to remember all the stuff that we're talking about. You can say accept, yes, no, and make some notes on the checklist. Again, it's a typical FHWA form. This, I forget if this is Paul's out of the drawings. I don't know if it's a note or a spec, but basically it says the contractor has an obligation to produce a template that ensures the orientation of the cage is where it needs to be. And the whole reason being, at the top of this drilled shaft, we'll have these longitudinal bars sticking up out of the ground, basically. Well, we got to build a reinforced pile cap that ties all four or all two of these shafts together. That reinforced pile cap has all sorts of reinforcing in it as well. So the reinforcing bars that are going in two directions in their cap have to fit in between all the steel that's sticking out of the drilled shaft. And so if you get the alignment off a little bit, the bars that have to cross transverse to it don't fit. All right, now we're going to talk about concrete. As we said, all drilled shaft concrete is essentially self-consolidating. We don't usually put a vibrator down to consolidate concrete in a drilled shaft, even in a dry hole. A Red Wing will be wet holes. So we're going to talk about some of the characteristics that concrete needs to have. Filling ability, we've already touched on it a little bit. It seems simple. We're putting fluid concrete in a hole, it'll fill up. But remember, we're putting it through a 10-inch trimmy or maybe even a 5-inch pump line, depending if they use a closed pump line. So that concrete's got to flow a long ways radially. And so we got to have concrete that has the ability to fill the shaft, to fill the entire cylinder. It's got to have passing ability. It's got to get through a cage. You've heard us harping about spacing of the hoops and the longitudinal bars. Well, those together make it a cage. It's like a bird cage. We got to get concrete through the bird cage. We need concrete on the outside of the cage just like we need it on the inside of the cage. It's got to compact under its own weight. Like I said, we're not numbers 2 and 3. We don't have any ability to put a vibrator down there. Oftentimes, to get desirable characteristics 2 and 3, you may end up with a concrete that is not very resistant to segregation and bleeding. If it's too runny and you got a pile of gravel or a pile of sand and we don't have a good cohesive mix, segregation and bleeding, that can be a problem. So we have to consider, to satisfy 2 and 3, we don't want to expose ourselves to problems of segregation and bleeding. Resistance to leaching, self-explanatory, controlled setting. Okay, so we want it to set in a time that works for our schedule. This shaft could take, I don't know, a day to pour, 8 hours to pour. I don't know what the rate will be. Maybe a shaft takes 8 hours to pour. So we want to have some control setting of the mix to allow that long duration of pour. It's got to be durable. Acceptable heat of hydration, of course. We don't want to. We've talked about some of the mass concrete concerns. We want to have this within tolerable limits. And obviously, we're using it as a structural member, so it's got to have the appropriate strength and stiffness. So we're asking a lot of drilled shaft concrete, but we've had success. The industry's had success being able to satisfy those demands. SCC, again, it's a mix design with extremely high workability. It's a runny mix. It's a runny mix that, when done right, isn't prone to segregation or bleeding. From a job in New Jersey, this was the spread. So instead of measuring slump, and I got photos later, we're measuring the diameter of the patty. Okay, so you can see the tape measure. We're measuring the patty. This was just a simple device to kind of mimic what longitudinal bars would look like, to see how the concrete would run around through the bars. The coarse aggregate in SCC is much smaller than typical coarse aggregate we'd see. You know, it's not a 1-inch coarse aggregate. It's not a 3/4 inch. Typically, it's a 3/8 inch mix. I've seen 1/2 inch, but typically it's a 3/8 inch. This is a little more granular, or a little more bony, I'd say. It's a crushed stone. Typically around here, you'll probably see river rock that's rounded, which is better. Precast yards use it. There's been some well-documented use for above-grade structures using SCC, so it's not uncommon in the industry. Its primary benefit is with congested reinforcement. So if you've got a really tight spacing, say you can't avoid the tight spacing, you need a lot of steel for ductility or for seismic concerns, things of that nature. SCC can be a great tool to use to allow your cage spacing to be a little tighter. Personally, in my opinion, the cage that Paul's designed has enough opening where we probably could get by without a SCC mix. If we had a 10-inch, 11-inch slump traditional mix, I think we could achieve the same thing. But MnDOT's got some good experience on recent projects with SCC, so they're going with it here. No problem. So that's the mix, or that's the SCC that was used at St. Croix. You can see the coarse aggregate is about 3/8 inch diameter, and it's rounded river run rock. So it's not the crushed stone. It means it flows a little bit better. It requires Super P and a lot of other admixtures. It's the Betty Crocker recipe, and it's easy to get the recipe off. So I'm always, well, I guess I'll get to it in the problems here, but higher content of cementitious and filler material. So you've got your proportion of Portland cement or slag is quite a bit higher for this SCC mix. Smaller, more rounded aggregate, we've covered that. So of the aggregate, about 50% of it, the ratio between fine to coarse aggregates about 50%, so a little bit different than a traditional mix. Lower WC ratio. Some of the problems we'll see with SCC, I'll just start out by saying when the mix is good, the project is great. When the mix is bad, it goes to hell in a handbasket. I mean, it's not like a mix where it shows up on site and it looks a little stiff, so you add 40 gallons or whatever to the ready mix truck and it keeps mixing. I'm not a fan of trying to doctor any SCC mixes when it arrives on site. There's so much that goes into the Betty Crocker recipe, it's too easy to get it screwed up on site in my judgment. So it's temperamental. So I mean, I guess I had a long one to say. It's a temperamental mix. I mean, it's great when you get all the proportions right, but boy, it can really cause problems too if you don't. Workability retention, by that we mean a shaft that takes a day to pour. We want to make sure we're not flash setting anywhere. We want to keep that concrete alive during the entire pour. We want to keep it alive during the entire pour. So that's asking a lot of concrete for a big shaft. It takes a long time to pour. Slump flow test, picture on the left. Anybody notice what's wrong from what's that compared to a traditional slump test? It's upside down, exactly. So I've seen this both ways when they measure the patty flow. Either upside down like this. I think this is more common. So this is a little cheater board. I mean, it's easy enough. They got the different diameter. You don't need anything this fancy. A piece of plywood will do just fine with the concentric rings, that is. So you fill the cone up, whether it's right side up or upside down. You lift it up, in a nice, smooth, slow motion, and then you throw your tape measure across it to look at the diameter. Red Wing specs allow 18 to 24 inch. Personal opinion, we're better off in that lower end of that range. I think 18 to 20 inches is about where you want to live, but they're allowed up to 24 inches. And I know MnDOT's used that range before. St. Croix was 24 inch, I think, and it worked fine. Something that's also required on Red Wing, admittedly it's a bit subjective, but I think it's a very useful tool. This was actually developed by the concrete industry, and it's kind of a visual way to qualitatively assess the quality of SCC. So what we're looking for is what we call this highly stable, or VSI 0, Visual Stability Index 0. And what that means is there's no evidence of segregation, there's no evidence of bleeding, as you see, the slight bleeding is observed as a sheen. See how it's a little more shiny on top of the patty? Okay, that's a little bit of slight evidence of bleeding. Red Wing will require a VSI of 1 or 0, so it's stable or highly stable. So you can see that little bit of sheen, that's acceptable. But once we start to get unstable, you see there'll be a halo of fluid, of nothing but cement-colored water around the edge or around the circumference of the patty. That will give you some indication that we're going to have trouble with bleed. Or if you see this pile of coarse aggregate right in the center, you know we're going to have some segregation concerns. So it's a very simple, albeit subjective tool to look at, and you can have a good idea of what you may expect. The batch plants will probably have an individual on site, and they'll probably, if you say it's VS1, they're going to VSI 1, they may say, well, no, it's VSI 0. Okay, we're in the ballpark. We're talking the same language. But if there's a disagreement between, say, 3 and 1, then we have to, put our foot down, I guess, and not let the job be run by the batch plant. Typically, though, I think they're very attentive to what the requirements are. Bleeding and segregation, honestly, I haven't had problems on his job with bleeding. I know that has occurred, and I know John's got some experience with bleed, especially with big drilled shafts that have permanent casing. The bleed water, if it's being developed, doesn't have anywhere to go outside. It can't get through the can, so it wants to come up to the surface. it either usually comes up on the right at the casing interface or up one of the longitudinal bars, path of least resistance type thing. This guy, you see some bubbles coming out of you can barely see it, but bubbles coming out of the top of the shaft. And then when you core, like say you got some squiggly lines in your CSL or tip or your non-destructive testing, you go and core it looking for anomalies. You see some evidence of bleed in some of the recovered core. Okay, so you've heard us talk about passability and how we want to make sure the bird cage isn't too tight. Well, I mean, these are some extreme examples, but certainly examples that have happened. So drilled shafts where the concrete mix, you could blame it on probably several factors. The mix was too stiff, didn't have the right passability characteristics, the cage was too tight. So lots of things that go in that are real, that turn out to be real problems. And so you can look at this picture right there, and this is, Paul, let me guess where you think this part is, right at the right rock socket interface, right where the shear gets magnified. You can imagine how difficult it's going to be to get concrete through that, you know, especially underwater where you can't vibrate it and push it through there. So this is what we're trying to avoid, and we've done that by trying to bundle the bars, the hoops, and use bigger bars so that we can spread them out more. So, you know, we want to avoid this. Your cage shouldn't look anything like this. But if it does, let's red flag it before we pick it up. Some things that you can see, you know, the concrete obviously is not getting through the cage here. Like I said, you could blame that on the cage or the mix, or probably both, to be honest with you. But there's really no reason to have shear hoops that tight together. So we want concrete that can get through it, but we want to have a cage that allows the concrete to get through it as well. SCC will help you with this, for sure. Acceptance testing, what's going to be required? Slump. For most drilled shafts, it would be the slump test. That's a very typical traditional test. Red Wing will have a flow test. That's more common with SCC, but it's using the same apparatus, a tape measure and a slump cone. Visual stability index, subjective, but a pretty good indicator. Air content, you know, the little device you fill up and you pound a few times with the mallet, check the air content. Temperature, obviously that means when it shows up, what temperature is it when it shows up. Strength test cylinders, those are old hat for everybody. You know, you make the cylinders, you let them cure, then you take them to the lab, bust them. All right, we've touched on this a little bit, and so I've got some, you know, we've said that we want to, when we're placing the concrete, we want to establish flow in a uniform manner so that the latents or the bad material that's left in the hole, if any, the contaminated concrete rides up on top. I can tell you from experience on these larger diameter shafts, it doesn't work quite that simple. When we put the trimmy down, we initiate concrete. If we've got a cage and concrete with inadequate passability, what we do is we build up a head around the trimmy. And then that head, once it gets to a high enough point and it can work its way through the cage, it splashes over. Well, when that splashes over, it traps all the junk that was supposed to be riding up on top. So we want to avoid that. We want the concrete to come up in a nice uniform manner. Just because we want that doesn't mean it always happens. That's why cleanliness and all that is still and overpouring is still a very important piece. We want it to come out nice and smooth and for the concrete to pass through the cage so it come up nice and sweet like the picture on the right. So I'll give you a little anecdotal information. This is from a test site, a national test site at Auburn University. A drilled shaft, 6-foot diameter, 30-foot deep, that was built. So why the dimensions are important. A 6-foot diameter shaft, every yard of concrete that goes in the hole is equivalent to about 1 foot of shaft. Okay, and so 3 10-yard trucks came to fill it up, and each load had a different dyed concrete in it. So the idea was to place the dyed concrete in the trimmy, pull the shaft out of the ground after it's built, and cut it open to see where the concrete went. Okay. So when we pulled the shaft out of the ground and cut it open, you can see that the concrete did not come up, and this was SCC. The concrete does not come up uniform like we would hope that it does. In fact, it probably does out by the cage for SCC, but really what you see last here, the last thing to get filled is the trimmy. So that embedment in the trimmy, that 10-foot embedment, when that trimmy gets pulled up, that's the last thing that gets poured. So what that means is we want a concrete mix that stays alive throughout the duration of the whole pour. So if it takes 8 hours to pour a shaft, we're not sure that concrete is going to be placed at the same time as that concrete next to it. So we want them to stay alive, a compatible amount of time. Also a reason why, and I think we have this in the spec, Paul, I can correct me if I'm wrong, about we don't want the trimming to be more than 30 feet embedded. So typically you see a minimum of 10 feet embedment to keep the seal, but we also now with information like this, we're limiting the amount the trimming can be, because with SCC you could conceivably have it all the way at the bottom. The concrete's so runny. But we don't really want that to happen because this is what is going to result, where we have basically concrete placed that's curing at a different rate. So there's limitations on the depth, minimum and maximum of the trimming embedment. Workability retention. Okay, so this is a chart, a pretty common chart that John's used in the NHI courses. We want the shaft concrete to stay alive throughout the entire pour. We don't want it to get out here for time after batching and then set up our flash set or anything like that. We want it to be alive throughout the entire pour so that we get compatible setting between all the concrete in the shaft, including where the trimming was at the last point. Now I will say these curves, which are of course a little bit arbitrary here, it's different in El Paso in July than it's going to be in Virginia, Minnesota in January. They're going to set up at different rates just from a temperature standpoint. So it's on the contractor to come up with the mix that stays alive throughout the whole duration. But workability retention is an important piece of the pie. So what do you guys, or what's the inspector supposed to do during concrete placement? I would say, and we always recommend that the drilled shaft inspector be someone independent from the concrete person, because the concrete person is going to have their hands full measuring all the concrete stuff, making cylinders, running the slump tests, doing the air content test if that's going on. And the drilled shaft inspector is measuring the depth to the top of fluid concrete, seeing where the trimming is and making sure that it's embedded the proper amount. So a lot of different things, do two different roles really. And in fact, one person might be on the bank and the other person might be in a man lift measuring. And so it's not very common, or it's not very practical for the guy in the man lift to come down, catch a boat ride back to the shore to make some cylinders. All right. We've seen this before. David's shown it a couple times. We want to get the trimming to the bottom, a watertight trimming to the bottom. When we place concrete, we got a pig, probably a Nerf ball. That's just to separate the water that's in the trimming from the concrete. As the concrete gets loaded, it pushes that Nerf ball down. The Nerf ball either floats up to the top or maybe half the time gets caught in the cage somewhere. It's not a problem. A Nerf ball under 80 foot of concrete head is probably about that big, so it's not a problem. It can stay. If it doesn't come up at the top, don't get too worried about it. But we initiate the concrete flow, so the pig comes out, concrete starts, we build up our head, we keep our 10-foot minimum, 30-foot maximum, and we keep going until that shaft is full. A question came up, Paul, about how do we check the embedment. So this is a little simple diagram about how do we make sure that we got that 10-foot or 30-foot max in the concrete. So our trimming should be marked with increments, 1-foot increments. We know how long the trimming is. We got someone up there making weighted tape measurements, feeling the top of concrete as it's coming up, usually relative to the top of the permanent casing. That's usually our benchmark, everybody's benchmark for drilled shaft work. So the difference between these two measurements is the length of embedment. Simple calculation. So the drilled shaft inspector should be monitoring the depth of the concrete to concrete relative to the trimming. So sort of a little cartoon here. We got a concrete and our trimming's in place. What we don't want to happen is for the trimming to get above the level of the fluid concrete. If we do, and we drop that concrete through the drilling fluid, water, slurry, polymer, bentonite slurry, doesn't matter what, we wash out the cementitious material, we get left with a pile of aggregate. It will show up on the non-destructive testing. When we go to core it after that, we'll get no core recovery in that zone. It's avoidable. We don't want this to happen. So it's just a simple arithmetic to make sure it doesn't happen. It's important to know the length before and have it marked. Yeah. Okay, we've Been through this before. Make sure the contractor uses a pig. This is just a device that separates fluid concrete from the drilling fluid. Case commonly uses what's called vermiculite. It's basically a substance where they take a 5-gallon bucket full of it, pour it into the top of the trimmy hopper, and it's almost like cork. It becomes like cork-like material. And so then you add concrete to the top here. It pushes that down. It's just a separator between water and concrete. Once it gets to the bottom of the trimmy, it goes away, and your concrete pour is now started. My personal favorite is the old-fashioned Nerf ball. I've just used it the most, and I've got the most comfort level with the Nerf ball. An air ball has worked. David, this was your project up in New York. I've never seen just an air ball work, but I can see how it would work. So I always take a picture just to make sure that I document that there's a separator. If the contractor didn't use a pig, because it's an easy thing to forget. Remember, it's a pour day, right? There's hundreds of people running around like crazy. A lot of things going on. It's easy for them to hook up the pump line and forget this piece. So I always make sure I take a picture of it, because what's going to happen if it's not there? At the bottom of your shaft, you're going to have anomalies. It's going to be gravel and sand down there. Your non-destructive testing is going to pick it up, and you're going to think to yourself, well, man, what happened? So you go check the logs. How can I post-mortem, how can I figure out what happened so that we can avoid it in the future? If I take a picture of this going in, I know that's not the fault. So I try and take a picture of that every time I'm on a job site. Before we begin the concrete commencement, again, make sure we got final depth. Need the final depth for lots of things. Your concrete volume curve. We're doing it to make sure that between the time of final cleaning and cage installation, which could take up to a day. I mean, some of these big cages, especially ones that need spliced, they can take a long time to get a cage in the ground. There's a shaft in San Francisco right now, 300 some odd feet deep. How many splices is that? 5 splices? That's probably an 18-hour.
Yeah, they were 60 foot.
So 5 splices to put a cage in the ground. I mean, that could take 2 days to put the cage in the ground. So, I always want to do a weighted tape measurement after the cage and right before concrete to make sure if it's not clean, pull the cage. You're better to do, if that's a headache and it's a nightmare, but it's better than risking a bad shaft. Is the trimmy watertight? We made lots of mention about this pig separating the concrete from the water. Well, you put the trimmy in the ground or in the slurry, and water's coming in through the joints because it's a segmental piece of pipe generally. It may not be at Red Wing because they're pretty short, but usually it's a segmental piece of pipe that's put together. If there's water flowing in, that's the same thing. We're introducing water that's going to be washing our cementitious material out. We're going to be left with poor quality concrete. Is the trimmy within inches of the shaft bottom? So when you start that pour, you basically want the trimmy sitting on the rock bottom or the bottom of the shaft before the pour starts. And then to initiate the pour, you raise it up a little bit, the pig comes out and the concrete starts. If you let that concrete drop a foot, 2 feet through water, again, we're washing aggregate. We're going to find that. You're going to find that in the non-destructive testing. A lot of stuff's going to happen once that first truck starts dumping into that hopper or that pump truck. It's going to go quick, so you got to be ready. And once you start, you're better off if you don't stop, unless there's a problem. Okay, so what if there is a problem? What if the mix is setting up and you're in the middle of the pour, the mix is setting up, okay? And so you can't pump it. Every time you pump it, it's trying to lift the cage up or the trimmy's bouncing around and you got a bad mix going into the ground. Well, you've already started. What do? The best thing in our judgment to do is to stop the pour, pull the cage out, which is a real headache, especially if you got to splice, unsplice. Remove the fluid concrete with the drill. So get the drill back on there while the concrete's still fluid and start over. There are contractors that would not do that, would try and pull the trimmy out, clear it, hit it with a sledgehammer a few times, stick it back in and keep going. It doesn't work. It's not allowed in the spec and it doesn't work. Zoo Interchange in Wisconsin, we're coming off a job with, Walsh was self-performing those jobs. That happened to them a few times and sure enough, you stick that trimmy back in, you're bringing problems with you. And that's right. You pull it up, it fills with water, and you stick it back down, and you've got a zone that's contaminated. And so it doesn't work. It never hardly ever works. Another option that I'm not saying it's what I have seen it done before. When you have a permanently cased shaft into rock, if you've started the shaft, the pour, and the concrete level is up, say, 20 feet or something into the permanent casing. So the rock socket, the uncased portion is poured. The casing's got a lot of concrete in it too, but you still got a ways to go, say. What you could do is pull the trimmy out right there, stop the pour, and let that concrete set up. You could come in later, pump out the drilling fluid, because there's still going to be drilling fluid on top of that concrete. Pump all that out. Send a person down with a chipping hammer to chip the bad concrete off the top of that and finish the rest of the pour in the dry. We've seen that done. It works. There's a cold joint in your shaft, but the shafts are designed to crack anyway, right? So the cold joint's usually not a deal buster. So we have seen that done before. This is the primary one though. Stop the pour, pull the cage, get the concrete out of there before it sets up, and let's take a breath and attack it again tomorrow. Okay, it's not allowed in the spec. Reinserting that trim is not allowed in the spec. And even if it were, it doesn't work. It rarely works. If it works, it's probably because there's no non-destructive testing on that job. Placement log and volume curve. David's been over this extensively, but we've got a few examples of what it really means to build one. The neat line, that's just the theoretical volume of the shaft, and the place line, that's the volume of concrete relative to the depth of the shaft. How do you plot it? On the y-axis, you've got elevation. You could use depth. And then you know the concrete volume per foot of shaft. Yeah, like I said, for a 6-foot shaft, that Auburn site, about 1 foot of shaft was filled up by 1 yard of concrete. So it's simple arithmetic to come up with the neat volume. So you plot the neat line. First point's at and the elevation minus 10, that's the tip of the shaft. Haven't placed any concrete, so that's an easy line or easy point to plot. Next one, say it's a 60-foot long shaft. It would take whatever that is, 35 some odd yards. There's your neat line. Simple enough. Now we plot the actual line. So after each truck, and so you have to know, are you using 8-yard trucks or 9-yard trucks or 10-yard trucks? So there's a little bit of guesswork. I mean, especially the last truck when it leaves. Say it, you have someone poke his head in the back of the hopper and it says, well, he left with 5 yards, so you used 5 yards. So it's a little bit of a guess on the last truck. Or if you have to send away a truck, maybe he pumped a couple yards. So there is some estimation work, but it gets you close. So after each truck or each known volume, measure the depth to the fluid concrete. That's your point. And connect the dots, and so there's your actual curve. Okay, now you got to figure out what that curve tells you. So here, this is our neat line. So when our lines are parallel, it's as expected. The volume is as expected. Where we have a bulge, say we wallowed out a hole, the slope of the line goes this way, right? So we've got more volume to fill up that certain length. Okay, then we're back to as expected, okay? So our line, although it's showing more volume is in the hole than the neat line, it's still the slope of that line is similar to the slope of that line, so it's as expected. Again, another bulge, so we get a slope increase or decrease, as expected. Now what happens when you get a neck? Say the soil was caving in on you a little bit, and so you got a neck here, which is what we don't want, of course. What you would see is the slope of this line, it approaches vertical. It becomes more like a vertical line. So what we're looking for is for this little pink line to be below the neat line and parallel with it, or parallel or lower, right? The lower angle. So it's a very simple, very quick. With Excel, like David said, you can be doing this as you go. And on engineering paper, you can do it too. I mean, in the old days, maybe not that old, but we did these by hand all the time coming up through where I cut my teeth. Another example, and I won't go too far into this, evidence of a cavity, that's pretty typical, like especially right at the bottom of a casing. Usually there's a walled out area right at the bottom of a casing, in soil. And so we see sometimes a big bump in where the casing stops, a bulge right here, again where the casing is. So you can see you got two different shafts at the same job. They both got the same neat line, and maybe they're different depending on bulges or what you found in that shaft. So before I move on, are there any questions with the concrete volume curve? It's a pretty simple concept, and it can tell you a lot of good from bad right away. I will say, in the permanent casing, the neat line we should be. Yeah. So if we know the casing dimensions, we ought to be able. Most of our shafts at Red Wing ought to be pretty darn parallel. Finishing, okay, so the overpour. We talked about the junk on top or the contaminated concrete that may be riding up on top. So on ground, no problem. Overpour it, scoop the bad stuff off till you see quality concrete at the surface, you're done. This can't happen at Red Wing because of environmental concerns. So you could either use a vacuum truck. These guys climbing down the cage with the suction into the hose, and they're going to suck up the remaining drilling slurry. And they're also going to suck up the bad acting concrete into the vac truck. These guys, this was at a Missouri River Bridge in Kansas City. The reason they're doing that down in the cage is if you have a job where your column splice is down in the hole inside a permanent casing or inside the top of a drilled shaft, by finishing the concrete below grade, it makes it really convenient to put your column steel down and lap it onto the longitudinal bars of the drilled shaft. So that's a real convenient way to finish the top of a drilled shaft when you have to lap on longitudinal bars to come up through your bridge bent. Let's see, same thing at Hastings there. You got the trimmy, the top of the slurry or drilling fluid that's being pumped out. The caveman way, a little more low tech, but probably the most common is when you're in a coffer cell and after things have set up, you get down there with the chip and hammer and the people that you don't like, and you make them beat the hell out of the shaft, try and protect your bar as best you can, and you beat up concrete until you find good concrete. You can imagine this is, not all cases can you even get tracked equipment, even though this is a little baby tracked equipment, and not all cases can you get equipment down in the holes. Most time it's a guy with a chip and hammer with a mask, respirator going down there and, doing the dance. And then some guy with big forearms pulling up 5-gallon buckets of concrete rubble. You're probably sick of seeing checklists, but there is another checklist to make sure that you can remind yourself not to overlook anything. Another FHWA typical checklist for concrete placement. And there is good information. I don't mean to demean the value of these. There is good information here, and they ought to be utilized. So part of our work that we do around the nation, we get a lot of phone calls when things go wrong, and so shafts that problems have occurred, and we get asked all the time what to do about them. Either we have to investigate further to see if there is a problem, or do some engineering analysis to figure out if it's a problem, and then if it is a problem, what the fix is. I underline real here. Non-destructive testing, be it CSL or thermal integrity profiling, they are indicators, quality assurance indicators, and so they're not certainties that there's a problem in your shaft. That's why they use the word anomalies. So after the shaft is poured and cured, when you do the non-destructive test, if it indicates an anomaly, that means there's a question somewhere. And so usually at that point you go and core the shaft with a little typical geotech investigative rig. You core the shaft, and you're looking for real anomalies. So when I say real, I mean not an anomaly that the CSL said you had, but one that was confirmed by coring. The whole next lesson is about non-destructive testing. Typically, the work that we do, or the ones I've been involved with, usually it's because either the trimming's too far off the bottom, so it's 2 feet off the bottom, or 3 feet off the bottom, so that 3 foot of free-falling concrete through water causes a problem. Bottom's not clean. If it's not clean, I think you said when it's not clean and that concrete starts, it pushes all that junk to the side. It gets trapped behind the cage. Well, the cage, guess what? All of our non-destructive testing tools are attached to the cage. So we see it out there. Trimmer removed and reinserted. This happened to Walsh a time or two at the zoo interchange. It didn't work out for them. I mean, the tip and the CSL indicated a problem. And then when we cored it, yeah, there was a problem. Leaking trimming, okay, especially with SCC that's more workable or more fluid or runny, I should say. If you got water leaking into your trimming, it can be causing some segregation essentially, or washing of the fines. Dirty drilling fluid. You've seen that picture of my hand on top of the SID with all that silt. Specifications right now for drilling fluid include requirements for sand content. There is no language about silt content. Okay, so if you've got a 200-foot deep, 12-foot diameter shaft that's got, I don't know, hundreds of yards of concrete to place, it could take you all day to place the concrete. Well, imagine all of that silt that's precipitating out of that fluid column as you're placing concrete. And it's all getting trapped, it's all getting folded into the concrete if you have dirty drilling fluid. So even if you go by what Paul was saying earlier, 1% sand content in a polymer slurry. Well, what's 1% of 300 yards? 3 yards. Okay, so that's 3 pickup trucks full of sand that you just dumped into your fluid concrete. Do you want that? No, we don't want it. So we got to have clean drilling fluid, especially on big shafts that take a long time to pour. And of course, bad concrete mix can be a problem too. Segregation, bleed, we've talked about all those before too. Those can be problems. Something that probably you may not have to deal, well, you won't have to deal with on Red Wing, but temporary casing. Folks, is temporary casing for like say commercial projects around here? Is temporary casing used for drilled shaft construction? Where they?
Yes.
It is. Yes. So you pour it up and then you pull the can.
We use it on our cantilevered signs.
Okay. So when you do that, if you pull, you got a concrete head that's fluid, and if you pull the casing, then all of a sudden the concrete disappears. You know, you can have problems with that as well. Things can cave in on top, and you got issues there.